Hello, welcome back to our Algebra 2 and Precalculus series. This lesson would be lesson 4, graphs and functions. And for those of you who already have a knowledge in Algebra 1 and Algebra 2, this should be still review. But for those of you who are new to this type of math, then this should be a good intro. Graphs and functions are a key part of Algebra 2 and Precalculus. So this is an extremely important lesson. Make sure to take good notes on this. With that said, let's start right in. First of all, we need to talk about the coordinate plane, which is the two-dimensional plane. If you watched my geometry series, then you should be familiar with this. If not, let's get right in. So the coordinate plane is the two-dimensional plane that we use in both geometry, algebra 2, and pre-calculus. The x-axis is the horizontal line, while the y-axis is the vertical line, and the place where they intersect is the origin, 0, 0. Each quadrant is a portion of the plane formed by the axes. And let me draw the coordinate plane now. It looks something like this. So if this is the y-axis, vertical, x-axis, horizontal, let me actually label them, x, y. And the origin is this intersection, so it'll be 0, 0. And a quadrant. So they're Q1, Q2, Q3, and Q4, and they're labeled counterclockwise. Why counterclockwise? Well, in math, counterclockwise is usually the positive direction, especially in geometry. When we talk about rotations, a positive rotation would be counterclockwise, while a negative would be clockwise. So math just likes counterclockwise, I guess. So this is Q1, this is Q2, this is Q3, and this is Q4. So a point or an ordered pair on the coordinate plane is the location. So let me draw an ordered pair right here, maybe. And I'll use a different color to show it, so you're not confused. This, I don't know, it's 5, 2 probably. And I'll explain how I got there in a minute. The x-coordinate of an ordered pair, or the abscissa, you move x units right if positive, or x units left if negative. So note the absolute value. They're just saying that the distance is always positive. So if the value is positive, so let's take 5 right here. If the value is positive, then we move 5 units right. If it's negative, then we move 5 units left. We don't move negative 5 units left. We move 5 units left. And the y-coordinate or the ordinate, you move y units up if positive, or y units down if negative. So similarly, if we have 2, you move 2 units up since it's positive. But if we had negative 2, you would move 2 units down. And here's how we got 5, 2. Most coordinate planes have a scale, but I'll just create a scale right now. 1, 2, 3, 4, 5. There we go. It's right on 5. And 2, 1, 2. There, it's on 2. So I'm going to switch colors once again. 1, 2, 3, 4, 5, 1, 2. And so that's the point. 5, 2. Some important formulas. Again, I talked about this in my geometry lesson, but this will still be a good refresher. The distance between 2 points. We can use the Pythagorean theorem to prove this. Actually, we did use the Pythagorean theorem to prove this in my geometry lesson. But the actual formula, given 2 points, x1, y1, and x2, y2. So this is 1 point A, this is 1 point B. The distance between them would be x2 minus x1 squared plus y2 minus y1 squared. Everything's under the square root. And it's important to write this down or memorize it, whatever, because it'll be really useful both in geometry and this series. We can also use the Pythagorean theorem to prove it, like I mentioned before. Let's just say it was from the origin to 5, 2. I already drew half of it. We have the 2 legs of a right triangle, and we have the hypotenuse of a right triangle. Again, go back to our geometry series if you don't know what I'm talking about. but basically the hypotenuse is the longest side of a right triangle. And in this right triangle, these are the legs. So the Pythagorean theorem states that a squared plus b squared is equal to c squared, where a and b are the legs, c is the hypotenuse. So there, it's 5 units to the right, 2 units up. So it'll be 5 squared plus 2 squared is this length. And we have to square root it, which is why we have a square root over here. I'll erase this to conserve some space. But our next important formula, the midpoint formula. So this one, if we have 2 points A and B, the midpoint of them, M, you would have to take the average of each of the coordinates. So for the abscissa or the x coordinate, we would write x1 plus x2 over 2, because that's how we take the arithmetic mean or the average of two numbers. And for the y coordinate or ordinate, we do y1 plus y2 over 2. And that's just it. So we had 5, 2 and 0, 0. We would do 5 plus 0 over 2, so 2.5, and 2 plus 0 over 2, or 1. So far we have this distance formula and this midpoint formula. If you want some more important coordinate formulas, then you can look into a geometry lesson about the coordinate plane, and I'll talk about distance between multiple points and other important formulas. But for algebra 2, we don't need those. We just work on a 2-dimensional plane. So anything else about the coordinate plane, we have to know about equations. So an equation we talked about in the previous lesson, an equation is basically setting two quantities equal. But we didn't talk about equations in two variables. All we did was stuff like x plus 2 is equal to 5. Now we'll be talking about x plus 2 is equal to y. So one variable, two variables. So it's not a coincidence that I chose x and y, because we have the x-axis and the y-axis. The x coordinate and the y coordinate. Oh, sorry, that was horrible. Anyway, so the y coordinate represents vertical distance and the x coordinate represents horizontal distance. So an ordered pair x, y of an equation represents the solution. X units horizontally, y units vertically. The x-intercept is a point where the graph intersects the x-axis, and is basically when y is equal to 0. The y-intercept, on the other hand, is the point where the graph intersects the y-axis, and it's where x is equal to 0. So yeah, I know it's confusing. X-intercept, y is equal to 0, y-intercept, x is equal to 0. But if you want to remember conceptually, it's x-intercept intersects x-axis, y-intercept intersects y-axis. To graph an equation in two variables, I'll actually do an example of this, so I'm going to have to clear my beautiful equations on the side. So to graph it, we plot the intercepts or any ordered pair that we can find and connect with a line or curve. So we'll probably be talking about this later, but there are different types of equations. And the most common one you'll see is something like this. Y is equal to 3x minus 5. So this is called slope-intercept form, and it's interesting and it's very useful because it gives us the y-intercept. But let's pretend we don't know that it gives us the y-intercept because we didn't talk about slope-intercept form yet. If we want to find the intercepts to graph it, first let's do y-intercept, the point where the graph intersects the y-axis. So how are we supposed to know that if we don't have the graph? Well, that's why we also have x is equal to 0. So when x is equal to 0, what is y equal to? Y is equal to 0 minus 5 or negative 5. So y is 0, negative 5. Right here. And the x-intercept when y is equal to 0. So now 0 is equal to 3x minus 5, And if you solve this equation as we did in our previous lesson, you'll get x is equal to 5/3. And I'm sorry for the horrible numbers, but it's all just the same. Even if I had like y is equal to x minus 5, it'll just be an easier equation to graph. But in this case, all we need is this 2 points. If we had a scale on the graph, which most graphs do, it'll be much easier to graph them. We since this is just online lesson, I'm not going to spend 5 minutes trying to make a scale for this. I'm just approximating this -5 and this is 5/3. So now I'm going to switch colors and draw the actual line. So since this is called a linear equation, we talked about this last lesson. A linear equation has a degree of 1. A linear equation is always a line. So I know that didn't really connect the 2 points, but this is approximately what our graph would look like. To graph nonlinear equations, you would have to get more points. So quadratic is something we talked about last time. And the graph of quadratic looks something like this. So it's not a straight line, it's really weird. For a quadratic, you need 3 points. This point, why not? This point, and this point. I don't know. But once you get those points, then you can connect it. If you don't know how many points you need, just graph as many points as you need, and then you can connect it. We spent a lot of time on the coordinate plane, but that's only because it's such an important concept to know. We'll still be talking about the coordinate plane for the rest of this lesson, but in more discrete ways. So now we'll be talking about circles. A circle is the set of all points that lie a given distance from a given point. This is basically revisiting geometry. The center is the given point and the radius is the given distance. So if I were to draw a circle or like this is the center and this is the radius. So the radius, each point over here is the given distance from the given point. So a circle on the coordinate plane, well, the center radius form is basically the main form of circles that you'll see. And it basically says that this is the x coordinate of the center, this is the y coordinate of the center, and this is the radius. So if we were given this, and I'll switch colors. If this was HK, the center, let's go back to our example of 5, 2, and the radius was 7, then first we'll go 7 this way, 7 this way, 7 this way, and 7 this way, until we get enough points to connect the circle. And voila, we have a circle on the coordinate plane. And all we need to know is the center and the radius. There's another form called the general form, and it's x squared plus y squared plus dx plus ey plus f is equal to 0. That seems much more complicated, but it is pretty useful. And the only reason it's pretty useful is because test makers love to try to fool you with this kind of form, and you can't graph it. You'll have to turn it into center radius form before you can graph it. So I'll actually turn this into center radius form for you. First thing, we know r squared has to be a constant. So the only constant here is f. Therefore, we can take it to the other side and we get x squared plus y squared plus dx plus ey is equal to f. Well, negative f actually. But negative f is not actually r squared, because how do we get from here to here? Well, we're going to have to complete the square. You might remember that from last lesson when we talked about quadratic equations and completing the square. First, we'll talk about the x's. So let's imagine that we didn't have any of the y's. So just x squared plus dx. So if you remember from our last lesson, we would do x plus d over 2, the whole squared. And since we had to add d over 4 to this, we would have to add d over 4 to this side. So I'm going to bring back the y squared plus ey for a second. And then we would add d over 4 to this side, as we did to, sorry, d squared over 4 to this side, minus f. And then we would have to ignore the x's and take only the y's. So then we had y squared plus ey. So y plus e over 2, the whole squared. And then we bring the e squared over 4 to this side. So we get d squared over 4 plus e squared over 4 minus f. And this is center radius form. In this case, the center is negative d over 2, comma, negative e over 2. And the radius is r is equal to square root of this thing. D squared over 4 plus e squared over 4 minus f. Sorry if that's hard to see, but the radius is just the square root of this. Easy. So I'm going to clear all my drawings, including the drawing of the circle and the coordinate plane. So yeah, that just summarizes everything I did in the last few minutes with one sentence. To center radius, complete the square. There are actually 3 cases if you're given the general form. If you're given the center radius form, it's obvious to see if it's a circle or not. You just see if h and k exist and if r is greater than 0. So if r is actually greater than 0, then it'll be a circle. But if it's equal to 0, then it won't be a circle. It'll be a point. And if r is less than 0, then it'll be non-existent. So that's easy enough for this. But for the general form, how do we do it? Well, again, we turn it into center radius form and see what r is equal to. I'm not going to bring back the center radius form conversion that I had, but if you should have taken notes on it. If not, you can go a few minutes back and see how I derived it using completing the square. So application is earthquakes. That's a bit concerning, but the main application of circles actually is earthquakes. And the epicenter is the center of the earthquake. So if we are given, if we want to find the epicenter, and we know that this, someone right over here felt this magnitude earthquake, someone right over here felt this, and someone right over here felt this. Well, we would just have to find the intersection points of the circles, and that would be the epicenter. I don't have an example right here, but if you want, you can try to create your own problem and find the intersection of circles. Note that if you only have 2 circles, then there will be 2 intersection points, unless they're completely tangent to each other. It can either be 2, 1, or 0. Or it can be all of them if they're just on top of each other. So if you really want to find one intersection point, best bet is to go with 3 circles. But then again, it's hard to find 3 circles with exactly 1. Basically, circles are weird. Functions. So this is the actual meat of the lesson. First thing, a relation is one quantity depends on another quantity. So you can do something like age, a student name and height. And note I have these curly braces, and that basically says that it's a set. It's a set of ordered pairs. So the input is the independent variable, the output is the dependent variable. If you watch the biology first lesson, I talked about independent and dependent variables. This is extremely similar. The independent variable is what you change, the dependent variable is your is what you observe. But in this case, it's the input, what you change, and the dependent variable is the output. So one way to look at relations is mapping. So for example, if I have 2 squiggly shapes, and I have, I don't know, John and an arrow connects him to his height, which is 5 feet. And then I have Bob, and he is also 5 feet. But then I have Jill, who's 4 feet, something like that. Now, I'm going to get rid of my example for a second because it's blocking. But now we're going to talk about a special kind of relation called a function. And it's when each input has exactly one output. So this is actually an example of a function because John can't have 2 heights, can he? But an example that is not a function would be age, student age, and student height. Because Bob, who's a 10-year-old, could be 5 feet, while Jill, who's also a 10-year-old, could be 6 feet. So it could be 5 feet. And Jill, who's also a 10-year-old, can be 4 feet, not 6 feet. It'll be kind of concerning if a 10-year-old was 6 feet tall. Then again, are 10-year-olds 5 feet tall? Oh, well. So the domain of a function is the set of values of the independent variable. And it's basically where a function is defined. The domain of any relation, it doesn't have to be a function. The domain of any relation is all real numbers that produce an output of a real number unless otherwise specified. So let's just look at the first part. So let's say we have a polynomial, x squared plus 3. I don't know. All real numbers that when you put into x give out a real number. But if we had something like square root, actually, no, that's a bad example. Square root of x, then if we put in x is equal to -1, for example, we'll get I. We talked about complex numbers in the last lesson, which is basically the square root of -1. But I is a complex number, not a real number. So therefore, the domain of this is x is greater than or equal to 0, because when you go less than 0, then you get complex numbers. Now we look at the second part, unless otherwise specified. So what if I had something like x squared plus 3, but I specify that x is greater than or equal to 0? Well, the domain isn't x is the all real numbers because I literally just said x is greater than or equal to 0. So that's kind of obvious. So the main functions for which the domain is not all real numbers is the square root and a rational function. So if I had something like x squared plus 3 over x, well, in this case, the denominator can be 0. So x is not equal to 0. All right. The range. So if we have something that is of the independent variable, we're usually going to have something similar of the dependent variable. So right, the range is a set of values of the dependent variable. The vertical line test is something that tells us if a relation is a function or not. So the vertical line test basically says that for every function, the vertical line, a vertical line actually, could be anyone, intersects exactly once. So I'll give you a function and you predict if, sorry, I'll give you a relation and you predict if it's a function or not. Is this a relation? Sorry, is this a function? Yes, because any vertical line you draw through it only intersects it once. What about this? Still, any vertical line only intersects it once. What about this? Our friend the circle over here. Well, if we draw a vertical line, it intersects it twice. Now, what if we draw a vertical line right here so that it's tangent to the circle? It intersects it only once. So is this a function? Well, no, because it should be any vertical line intersects it exactly once. But in this case, there's at least one vertical line that doesn't. So function notation is basically another nice way to write functions. So instead of writing y is equal to, I don't know, 3x minus 5, from our previous example, we write f of x is equal to 3x minus 5. And it looks a bit like this. Or since this is text, it's harder to see, but it's usually like this. Or you can also write g of x or h of x, but it's normally just f of x. Some cases, for example, when we're talking about physics, it's usually not x, which is the independent variable. It's usually time, which is t. So it might be like f of t. In if we're talking about physics examples, then that's what you'll most likely see. So another way to read this is that f of x is the output of the function for a specific input, x. So f of a would be for the input a. F of 2x would be the input for 2x. F of g of x, as we'll talk about later this lesson, would be when the input is g of x. A function is increasing. So this is how you describe some functions. This looks pretty complicated. What's x1? What's x2? It's basically, if we have something like this point is less than this point. So it's basically saying that if the x value of a point is less than the x value of another point, then the output of that point is less than the output of this point. So if we have something like 2 and 3, so 2 is less than 3, that satisfies that condition. Now, f of 2, or the output of 2, would be 4. Let's say this was a quadratic. This does not look like a quadratic, so I'm just going to talk about a different example. But f of 3 would be 3 squared, which is 9. So that also fits this condition, so it's increasing. Now, you might be wondering, what if I had x1 is 3 and x2 is 2? Then you just switch them around, and you get x1 is 2 and x2 is 3, and then you do the same exact thing. Decreasing is when it's the opposite. The output is of the smaller number is greater than the output of the larger number. So again, if we had, maybe we can do the other side of quadratic. So we had -3 as x1 and -2 as x2. Remember, -3 is less than -2, even though 3 is greater than 2. Remember that. So right, if we had -3 and -2, f of -3 would be 9. F of -2 would be 4. So this works. It's decreasing because 9 is greater than 4. Constant is basically when the outputs are the same. So if I had, what's a nice constant function? Well, there barely are any constant functions. So if I were to just create a function of my own, something like this, you'll probably see this in physics, like position time graphs. It's basically showing the motion of something. Well, in this area right here, it's constant because this point is less than this point, but their outputs are still equal. These are some good ways to describe a function, but what you'll mostly see in textbook is called the function machine. I don't really believe in function machines, but I'll probably just show it you so you have a better understanding of functions. So it probably looks something like this, and f of x is the name of the function machine. So let's just take x squared again. If we put in 1 as the input, we get in 1. If we put in 2, we get 4. If we put in 3, we get 9. Yeah, I don't have space to finish this, but still. This would be the input, and this would be the output. Let me just get rid of input, output. Oh, I don't have space. Oh, well. I hope you see the meaning of a function machine. It's probably the best way to look at a function if it's your first time, but if you're used to functions, just use f of x. So linear functions, we talked about linear equations. Now linear functions, f of x is equal to ax plus b. So a linear equation was y is equal to ax plus b. That's a linear equation in two variables. There's a linear function, which is basically that as a function, f of x. And all linear equations are functions. Similar to how we graph equations, you calculate 2 points and connect with a straight line. That's key over here, straight line, because like I said, linear equations are always straight lines. If you want, those 2 points can be the intercepts, but if not, you can just plug in 1 into this, and then you can plug in 2 into this, and then connect those two. So unless you have a horizontal or a vertical line, the domain and range are all real numbers. And now that we're talking about horizontal and vertical lines, the horizontal line, it's the constant function. So actually, this is a wonderful example of a constant function because it's constant throughout its graph. So let me use a different color to show you, but right, that's constant everywhere. This value is less than this value, but the output is the same. And it's written as f of x is equal to b. Oh. What's wrong with this? And a vertical line. This is not a function. Unless, like I said, all linear functions are, linear equations are functions unless it's a vertical line. And this is written as x is equal to c. So a graph would be something like this. This doesn't really look vertical, but it's parallel to the y-axis, so that's what counts. So right, the forms of a linear function. Standard form is ax plus by is equal to c. And this is pretty confusing because it's like the general form of the circle we saw. We can't really graph it unless we know the slope. So sorry, I revealed that, but first thing about the standard form, the greatest common factor between a and b is 1. It's basically saying that you can't have something like 4x plus 6y is equal to 8. You have to divide everything by 2, so you get 2x plus 3y is equal to 4. So right, slope. You can't really graph standard form without knowing the slope. And it's the measure of the steepness of the line. So a line that looks like this has a higher slope than something that looks like this. And slope is also called rise over run. You've probably heard this term before. And it's also y2 minus y1 divided by x2 minus x1. So here's the formula. I know it looks weird with that division sign in the middle, but if you want, you can write this down. This is the formula for slope, and it'll also come handy in calculus before we learn derivatives, or when we're trying to prove derivatives, I guess. The slope of a vertical line is undefined, and the slope of a horizontal line is 0. That makes sense because a horizontal line, the y values don't change, so it'll be 0 in the numerator. Vertical lines, the x values don't change, so it'll be 0 in the denominator, and we can't have 0 in the denominator, so it'll be undefined. The average rate of change is the same thing as slope, but this is when the function is not linear. So if I had a parabola that looks something like this, and I wanted to find the average rate of change from here to here, I would have to draw this. This is y2 minus y1, and this is x2 minus x1. And this would be the average rate of change, AROC, actually, for those of you who want to continue in calculus, AROC, the average rate of change of this function. Over a certain interval, of course, because it's not the same throughout the entire function. Linear models are some applications of linear functions, and they're used to approximate linear data. So for example, the cost function is equal to cx plus I, the revenue function would be r of x is equal to px, and the profit function would be p of x is equal to r of x minus c of x. Now, c and p can stand for different things based on what you're talking about. In this case, I believe that C would stand for the cost it takes to make one and make a certain item, and I would be the initial cost. So for example, if you're selling lemonade, it takes you $20 to buy, $20 to get glasses for each cup of lemonade, and it costs you $5 to get a whole bunch of lemons. That would be your initial. So the initial would be $5 because you don't need to buy that again. It's just one-time thing. And CFX would be $1.20 because it costs $20 for each glass. And revenue, let's say you charge $30 for each glass of lemonade. Yes, it's a bit overpriced, but we're living in an inflating world. The profit function would be the revenue minus the cost. So revenue is basically how much you get. So it'll be 30x, and the cost would be 20x plus 5. Another important form of a linear function is point slope form, and this is a bit easier to graph because it gives you the slope. And it also gives you a point. So you have one point and you have the slope. So let's say the point I was given was 2, 3. And I know the slope is -2. So actually, let's go easy and go 2. M is equal to 2. And this is basically rise over run. So if run is 1, then rise is 2. So if run is 1, that's 1 right there. Oh, that's a big one. If this is 1, then this is the rise, 2. So we found another point. So then we can connect these points. Oh, that's horrible connecting points to form a line. Voila, this would be the graph. And this is how you graph a point slope form. Slope intercept form is y is equal to mx plus b, and this is by far the most useful and most common form. I believe I told you about slope intercept form a bit, and here's how to actually use it. So we're already given the intercept. This is the y-intercept. That's why it's called slope intercept form. So let's say it was 5, I know, and the slope was 2 again. Then again, we can do the rise and run thing. As the run is 1, the rise is 2. So we found another point and we can connect it. And the usefulness of this is mainly because you don't have x minus x1, y minus y1. You just have a compact mx plus b. And parallel and perpendicular lines. So review a bit of your geometry. Parallel lines never intersect and are in the same plane. Perpendicular lines intersect at right angles. So if non-vertical lines have the same slope, then they're parallel. So M1 is equal to M2. Let me just draw an arrow. If non-vertical lines have slopes that are negative reciprocals, basically M1 is equal to -1 over M2. So M1 times M2 is equal to -1. Then they are perpendicular. Let me get rid of those for a second. I hope you took notes. So now modeling. So you make a scatter plot and find the equation, line of best fit. So that's basically modeling in general, not linear models, that's different, but modeling given a set of data, you want to try to find the line that fits it best. So let's say we were given a bunch of data about, that's a horrible set of data because you can hardly find a line of best fit in there. About children's heights. age versus their height. So you can use some sort of graphing calculator. Desmos actually does this, but you can find the line of best fit. And it's basically the line that is the average of all the points. And this is really useful when you're talking about modeling, because usually you'll see line of best fit, but sometimes it'll be exponential functions, sometimes it'll be quadratic functions, etc. And notice that the line of best fit, in this case, actually, I don't think it goes through any of the points perfectly. It doesn't have to go through any points, but it has to be the best line that fits the data, aka the line of best fit. Anyway, let me get rid of that. And so solutions of linear equations in one variable. If y1 and y2 are linear expressions in x, first thing to do is find the x-intercept of y3 is equal to y2 minus y1. Okay, that just confused you probably. But even though this has one variable, we're actually talking about two variables, y and x. We're trying to make it from two variables to one variable. So that's why it looks a bit confusing. We talk about one variable and then x and y, but we're just saying if we have something y1 is equal to ax plus b, y2 is equal to cx plus d, first you find y3 is equal to y2 minus y1. So this looks a lot like systems of equations. We'll be talking about that in later lessons, but in Algebra 1, you should have learned some topics. So if you subtract these, you get a minus c times x plus b minus d. And what you want to solve is this. We're assuming that y of 3 is equal to 0, because the solution of this is where they intersect. This looks a lot complicated, so I'm going to clear this right now, and I'm going to show you an easier way. Instead of dealing with y3s, you can just, oops, I accidentally cleared that too. Oops. Cx plus d, right? Since the solution is where they intersect, you can set them equal to each other because y1 has to equal to y2. So ax plus b is equal to cx plus d. And then we can use the skills we learned last lesson to solve for x. And that's a much easier way than to do this, but we're basically saying in this way, we're basically saying 0 is equal to a minus c times x plus b minus d. This is actually one step further into this. You can solve it whichever way you want, but it's best to know both. Some more on functions. Continuity is an important concept in functions, and it'll mostly be taught in calculus or precalculus, like late precalculus, the ending of precalculus, because we need limits to talk about it, and we'll only talk about limits in calculus and late precalculus. So continuity is when a function can be drawn without lifting the pencil, and you can probably guess what discontinuity is. It's basically when the graph cannot be drawn without lifting the pencil. So basically you have to lift your pencil. And notice when I say lifting pencil, that's basically like a child's definition of it, because when we talk about limits, we'll actually get into the mathematician's definition about it. But in Algebra 2, it's important to know about continuity without limits. So discontinuity is a break in graph. It can either be whole, a jump, or an asymptote. So a whole would be something like this. So this is a hole right here, if you can't tell. A jump would be something like this. Basically, there's no function over there. And actually a better example of jump would be something like this. There, now you can see it more clearly. And then the final one, asymptote, is something we'll be talking about when we talk about rational functions. And it's basically something like this. So x would never be equal to 0 because it's also called an infinite discontinuity. It basically keeps on going closer and closer to that, but it never reaches that. So piecewise defined function is defined by different rules over different intervals. So an example would be y is equal to x if x is greater than or equal to 0, or 2x if -2 is less than or equal to x, which is less than 0, or x squared if x is less than -2. So if I were to graph this, which I just made up on the spot, first, since this is non-strict, there's a closed hole. And then we can just draw y is equal to x over here. And then -2, right? So if this is -2, I like to draw little dashed lines over here to show where the discontinuities are, per se. So for -2, if you plug that in here, we get -4. And since this is non-strict, it's closed, and we can draw this. So this is actually steeper than this if you can't tell by the graph. And then finally, x squared, at -2, this would be 4. So this would be a jumped discontinuity. And then we continue drawing y is equal to x squared up there. So yeah, I know this looks messy, but on paper, it'll be much easier to see. Some major important functions other than the linear function. So identity is f of x is equal to x, square, function, quadratic, parabola, all same thing, x squared, cube, as you can guess, x cubed, square root is the square root of x, cube root is the cube root of x, absolute value is absolute value of x, greatest integer, this one's a nice one. So I'm gonna have to switch to a different color. And it's basically saying that it's the greatest integer less than or equal to x. So yeah, like the definition says. The input is x and the output is the greatest integer less than or equal to x. So if I were given x is equal to 0, it'll still be 0. For 1, it'll be 1. For 2, it'll be 2, 3, and so on, and down here too. But then what about the points in the middle? What about 0.5? The greatest integer less than that is 0. So until 1, it'll still be 0. And until 2, it'll still be 1. Until 3, it'll still be 2. Until 4, it'll still be 3. Until 0, it'll still be -1. Until -1, it'll still be -2. And so on and so forth until it looks like this. This is called a step function. And it's actually a piecewise defined function. If we were to write the equation of it, we would write it's equal to 0 if 0 is less than or equal to x, which is less than 1. It's equal to 1 if 1 is less than or equal to x, which is less than or equal to 2, and so on and so forth. And -1 if -1 is less than or equal to x, which is less than or equal to 0, and so on and so forth up here until it's infinite. Horizontal parabola, this is not a function, so it's actually misleading. Even though this has major functions, this is actually a relation. It's when x is equal to y squared, and it looks something like this. It looks like a square root function. That's no coincidence, as we'll talk about when we were talking about inverses. It looks like a square root function, but with 2 sides. So it's basically a parabola, but horizontal. Transformations of functions. So remember when we talked about major functions, we did something like square root of x, but usually we see something like square root of 2x minus 5 plus 3. And I don't know, why don't we add a negative half in the front? How are we supposed to graph this? Well, all we knew was the graph of this, which looks something like this. How are we supposed to graph that? Well, that's where transformations come into play. So vertical stretch if we're given something like, let's just take the squared example. If we're given this, then we add a number in front of here, we multiply it to the function such that it's greater than 1. And what this does is basically it stretches it vertically, in case you didn't know. So if the previous one was this, the new function would be something like that. I'll keep this here as we talk about this. Vertical shrink, let's just say it was one half times root x. Then this would be a shrink vertically. And then horizontal stretch, similar, but it would be something like this. 1/2 of each. 1/2 over here inside. And notice that the stretch is still a is less than 1. This looks like this. And then we have horizontal shrink, which looks something like this. 2x. So the function would be something like this. Yeah, I know it's hard to see on this. Reflection. So I'm going to get rid of all of this for now and talk about a different function. Doesn't that sound fun? X squared. So this is the original function. And now we're doing the negative of it. So it'll be reflection over x-axis. So it'll be something like that. Something like that. And then reflection across y-axis. Well, in this case, it'll still be the same function. It looks something like that because you're just reflecting it over the y-axis. And this, the negative x is inside it. So it'll be negative x squared. And this is basically x squared. So symmetry. Now that we're talking about reflections, something important of a function is its symmetry. So an even function is symmetric over y-axis. An example is x squared, as you can see. When you reflect it over the y-axis, it's the same thing. And it's basically saying that f of negative x is equal to f of x. Odd is when it's symmetric over the origin. And f of negative x is equal to negative f of x. And an example would be the cubic function. When you reflect it over the origin, you'll get this. The same function. Symmetric over x-axis is when it's not a function. And the most common example of this is the horizontal parabola. When you reflect it over the x-axis, you get the same exact function. Let me clear this so that I have some more space. Note that if the graph has two of the above symmetries, it also has a third symmetry. And this is really rare. It's probably some sort of double hyperbola that looks like this. Yeah, that has all three symmetries. So even if we prove that it has two of them, we can find that it has the third as well. So translations are final transformations. Vertical, you move it up if k is positive and down if k is negative. And horizontal, you move it right if h is positive and left if h is negative. So these are probably the most common transformations you see. It's probably worth it to memorize them, even though there are a lot, because in pre-calculus, transformations would appear a lot. When we move on to trigonometric functions like sine and cosine, the transformations would be even worse, trust me. So function operations. So if we can add 2 and 3, why can't we add two functions? That's basically what this is saying. So to add functions, it's basically saying that if this was x squared, why not? And this was x squared plus 3, then when you add them, you get 2x squared plus 3. You're basically adding them, combining like terms, etc. Same with subtracting, same with multiplication. Well, actually, with multiplication and division, it's a bit different because if we had x squared and x squared plus 3, then it'll be x to the power 4 plus 3x squared. Most of these would be polynomials, so we can use the rules we learned earlier. If not, I don't think you can simplify them. The difference quotient, this is extremely advanced precalculus. So if you're in Algebra 2, don't sweat it. It's the slope of the secant line of a curve. And this has to do with average rate of change that we talked about earlier. If we have the quadratic function, the slope of a secant line, let me switch colors, would be something like that. And see, it intersects it twice, so it's a secant line. Tangent lines, which we'll be talking about in calculus, would intersect it exactly once. So between P, so let me just label this P, it's x comma f of x and q x plus h plus comma f of x plus h. This looks a bit complicated, but it's basically the slope of the line that connects p and q. P and q are both on the function. As h approaches 0, the slope becomes the slope of the tangent line, which I told you about earlier. So basically, as q comes closer and closer to p, then q will be p, and there'll only be one point touching the parabola or the function. So finally, we'll be talking about composite functions in function operations. This is not exactly an arithmetic operation, but it's basically when you're combining two functions. If I have x squared and x plus 9, 2x plus 9, why not? And I want to see, this is what I told you about earlier. G of x is the input of f of x. So if this is f and this is g, then we basically plug g into f. So instead of x squared, it'll be 2x plus 9, the whole squared, which would be, if we remember from our review, it'll be 4x squared plus 36x plus 81. And you can also do it the other way. G of f of x would be, when you plug in x squared into that, so it'll be 2, and instead of x, we have x squared plus 9, which would be 2x squared plus 9. And composite functions would be useful when we're talking about inverse functions. That'll be a few lessons from now. The domain is all x in domain of g of x, such that g of x exists in the domain of f of x. Yeah, I know that's confusing, but it's basically saying that if x doesn't exist in g of x, then it doesn't exist in the composite function. As in the example previously, f of g of x is not always equal to g of f of x. This is key because most students confuse this up and they say that it's always equal to each other. It is not. It's not always equal to each other. It could sometimes be, but it's not. So that's it for today's lesson. Today we talked about graphs of functions and some major functions and what to do with functions. Next time we'll be talking about specific functions. Like I said, Algebra 2 and Precalculus are basically functions, different functions, learning about different functions. But next time we'll be talking about polynomial and rational functions. So thanks for listening. Bye.